So, you've probably used ChatGPT, Claude, or Gemini, right? You type in a question and bam, like magic, a coherent, often brilliant answer just appears. But have you ever really stopped to wonder what's actually going on inside that digital black box? I mean, how does a machine go from a jumble of code to composing poetry or writing software? Well, let's pull back the curtain and really demystify the AI brain one layer at a time.
It sounds almost way too simple to be true, but really, it all starts here. At its most fundamental level, a large language model is just an incredibly sophisticated autocomplete. I mean, think about it. After being trained on trillions of words from books, articles, and basically the entire web, it learns the statistical patterns of human language. Its one core job is just to ask itself, okay, based on this string of words, what's the most probable word to come next?
And that's the million-dollar question, isn't it? If it's just a prediction engine, just guessing the next word, how in the world does it get these incredible emergent abilities, like reasoning, following complex instructions, and even planning out multi-step tasks? Well, the journey from a simple word guesser to a powerful tool involves several layers of absolutely brilliant engineering. So let's start peeling them back.
Okay, the first layer, and this is the real engine behind this whole revolution, is a neural network architecture that was introduced back in 2017. It's called the transformer, and let me tell you, it completely changed the game. Pretty much every major LLM you hear about today is built on this very foundation.
But before the transformer can work its magic, your prompt, what you type in, has to go on a little journey. First, your text gets broken down into smaller pieces called tokens. These can be whole words or just parts of words. Then, these tokens are converted into a series of numbers or embeddings, which is a language a machine can actually understand. Only then does it get fed into the transformer network for processing.
Now, the transformer's secret weapon, its special sauce, is something called the attention mechanism. See, older models had to read text word by word, in order. The attention mechanism lets the model look at all the words in a sentence at the same time and decide which ones are most important to each other. This is how it gets context. It's how it knows bank means one thing in riverbank and something totally different in money in the bank. It's this incredibly complex web of connections that really captures the nuances of our language.
Okay, so we've got this powerful engine, the transformer. But a brand new engine, it doesn't have any experience, right? To become useful, it needs to be trained. And this training happens in two absolutely crucial stages.
The first stage is called pretraining, and this is a massive, self-supervised process. Basically, the model is fed a huge chunk of the internet, and its only goal is to predict the next word over and over and over again for trillions of words. You can kind of think of this as compressing all of the internet's knowledge into a base model. But this base model, it's just a raw document generator. To make it a useful assistant, it has to go through fine-tuning. This is where it's trained on high-quality Q&A datasets, often with human reviewers guiding it, saying good answer or bad answer. This is where it learns to be helpful, to follow instructions, and, to stay safe.
And this is the most crucial point to remember. An LLM is a direct reflection of the data it was trained on. The quality, the diversity, the sheer scale of that data, that's everything. It's what gives the model its amazing capabilities, but it's also where problems like factual inaccuracies or biases can creep in.
Now, there's a really big problem with a model that's trained this way. Its knowledge is static. It's basically a snapshot of the world from whenever its training data was collected. So how do we give it access to stuff that's happening right now?
A standard LLM, all on its own, has no concept of today's date. It doesn't know about yesterday's news or your company's latest internal report. Its knowledge is literally stuck in the past, which, as you can imagine, severely limits how useful it can be for real-world applications that need current information.
The solution is this really elegant technique called Retrieval-Augmented Generation, or you'll hear it called RAG. So instead of only relying on its internal, frozen knowledge, RAG lets the model first look up relevant info from an external source, like a search engine, a company database, whatever, and then use that fresh information to generate its answer.
So here's how that actually works. When you ask a question, the RAG system first goes out and searches an external knowledge source for any relevant documents. It then takes the key facts from those documents and injects them directly into the prompt as extra context for the LLM. So now, the model has the fresh, specific information it needs to give you a much more accurate and up-to-date response. It's kind of like giving the model an open book exam instead of a closed book one.
So far, we've pretty much talked about LLMs as oracles. They answer our questions. But the next great leap where things are headed is transforming them from knowers into doers.
And this is the exciting new world of AI agents.
An agentic workflow gives an LLM the ability to do more than just talk. It can actually take initiative, make decisions, and use tools to accomplish a goal. Think of it like this. It's the difference between asking a librarian for information and giving a research assistant a complex task to go and complete on their own.
So check this out. The user gives a complex, multi-step command. Describe this picture and count the objects. The LLM, acting as a controller or a brain, first plans out the task. It realizes, okay, I need to identify objects, and then I need to create a caption. Then it schedules the right tools for the job. It calls on specialized models for object detection and for image captioning. After it executes those tasks, it summarizes all the results into one single, coherent response. So it's not just answering a question, it's orchestrating a whole solution. This technology is evolving at an absolutely breakneck pace. It's hard to keep up. So as we wrap things up here, let's take a quick look at what the future holds, both the amazing opportunities and the immense challenges that are still ahead.
This timeline, wow, it really says it all. The introduction of the Transformer back in 2017 was the spark, but just look at the explosion of models in just the last few years. The pace of innovation is accelerating, not slowing down. I mean, what was state-of-the-art 6 months ago is often just commonplace today. It's wild.
Researchers are pushing on so many fronts at once. We're seeing the rise of smaller, more efficient models that can actually run on your phone. Multimodality is becoming standard, so models can understand images, audio, and video, not just text. They're being built with longer and longer context windows, which gives them a much better short-term memory. And of course, there's a huge focus on improving reasoning and finally tackling that persistent problem of hallucinations.
So we've gone from a simple next word predictor to a complex tool-using agent in just a few short years. It's a pretty remarkable journey when you think about it. But it really begs the question, as these models become even more capable of reasoning and acting in the world, what's the next great leap? And, more importantly, what's it going to mean for all of us?